A very good morning to all the students. I am Dr. Hima Bindu from the Department of Mechanical Engineering, and I'll be dealing the subject robotics in Institute of Aeronautical Engineering. In today's session, we will be discussing about few more examples of problem solving on various constraints. Right? So, in the first problem, we will be finding out the various lengths to be shown in the single link manipulator. Right? For a single link manipulator, how do we calculate the length? That is, let me read the question first. Compute the effective inertia, coupling inertia for a single link manipulator with a mass of m and length of a1. That is, here we need to find out the effective inertia. We need to find out the inertia, and we need to find out the effective inertia. We need to find out the effective inertia, and we need to find out the coupling inertia. Right? We need to find out the effective inertia, and we need to find out the coupling inertia for a single link manipulator. So that's how we will be doing with respect to the mass and the length being given. So initially, this is the manipulator which we are having for a robot, which is having an x-axis and which is having a y-axis. Here also it is having an x-axis, it is having a y-axis, that is x1 to y2. Right? So it is having a length of a1 and it is rotating at a mass m1. Right? So here, to compute the effective inertia, it has been taken as L effective and the coupling inertia is written as J effective. J suffix effective and I suffix effective will give the F. It is the determination of effective inertia and the coupling inertia. So for a single link manipulator which is shown in the figure, we need to follow these particular steps. That is, in order to find out the effective inertia with respect to the mass and the length, the effective inertia formula is I effective is equal to length, that is Iz, inertia at z, plus m1 d square. Right? Iz plus m1 d square is equal to effective inertia. Right? Effective inertia will be calculated with respect to the Iz plus m1 d square. Right? That is the effective inertia of a single link manipulator with mass m and length a is given by the inertia about the axis of rotation. Right? Now here, what do we mean by Iz? Iz is nothing but the moment of inertia of the link about its own center of mass. Right? Iz is the moment of inertia of the link about its own center of mass, whereas d is the distance from the joint to the center of the mass of the link. So for a uniform rod, when we are considering this particular uniform rod, we need to know how to calculate this particular moment of inertia with respect to the center of mass. So that is being given as Iz is equal to 1 by 12, mass 1 and acceleration 1. Right? So with this equation, we will be finding out where d is being considered as a by 2. Right? Where d is being considered as a, that is the center of mass is located at a distance center. Right? When we are taking the rod, the center of mass is being taken at a distance. That is, d is taken at a particular center distance, which is nothing but a1 by 2 for the joint. So thus the effective inertia formula will become as I effective is equal to 1 by 12. What is this? m1 a1 square plus m1 d square. Right? m1 d square, what is d square? It is I effective is equal to 1 by 2 I square is equal to Iz plus m1 d square. I effective is equal to Iz plus m1 d square. Iz here we have that we are inserting here, and d square, d value is a1 by 2, so that we have written this is nothing but d square, right? m1 into d square. So when we are simplifying that particular equation, what we are getting, I effective is equal to 1 by 12 m1 a1 square plus 1 by 12 m1 a1 square, which is nothing but 1 by 3. Overall, we are getting 1 by 3 m1 a1 square. That is, I effective is equal to 1 by 3 m1 a1 square. Now, we need to find out the coupling inertia. How will we find out the coupling inertia here? Coupling inertia is, again, we have written it as J effective. Now, the coupling inertia is nothing but the relevant multi-link system where the motion of one link is affecting the other, right? Where the coupling inertia, where the motion of one particular link is affecting the other. Then this is link 1 and this is link 2, and this is the joint 1 and this is the joint 2. So, when we are considering two manipulators, here links, here one link is affecting the other. That is multi-link system where the motion of one link affects the other link. So for that, the JF, therefore the coupling effectiveness is being written as 0, right? So here, as per the equation, I effectiveness, effective inertia is nothing but 1 by 3 m1 a1 square, and the coupling inertia is being taken as 0 joules. That is, for a single link manipulator, there is no coupling inertia since there is only 1 degree of freedom, right? When we are considering only one single link, when we are considering only one single link here, right? In this problem, what we have done, we have considered only one link. So when we are considering only one single link, there is no coupling, right? If we are having another link, there will be a coupling and we will be getting some other value. Since there is no coupling, the coupling value will be equal to 0, right? The coupling value will be equal to 0. That is what we have written here. J effectiveness with respect to the coupling is equal to 0. Thus, the result describes the inertial characteristic of a single link manipulator in the figure. That is, here we have got J I effective is equal to 1 by 3 m1 a1 square and J effective is equal to 0, right, for a single link manipulator. Right? In the given question, what we needed to find out, the effective inertia we needed to find out, and the coupling inertia. Since the effective inertia we can find out with respect to the mass and acceleration, we will be getting the effective inertia. Whereas we don't have any other link being supported to the given single link manipulator, the coupling will be equal to 0. Moving on to the second problem. Using the LE formulation, we need to determine the equation of motion for a revolute prismatic RP robot arm manipulator, which is shown in this particular figure. This is the RP manipulator. For this, we need to find, using the LE formulation, we need to determine the equation of motion. So, we need to determine the equation of motion, right? So, this is the solution. So, in order to determine the equation of motion for a revolute prismatic robot arm, we need to take down the Lagrangian Euler formulation. What is LE formulation means? It is nothing but Lagrangian Euler formulation. So, firstly, we need to know what is theta and what is at what angle it is rotating, or at what distance it has been moving from one place to the other. So, theta 1 is nothing but the angle of the revolute joint, and d2 is the displacement of the prismatic joint for the given RP manipulator, right? That is, T1 is the angle of revolution joint and D2 is the displacement of the prismatic joint at 2, right? This is the prismatic joint at 2. This is the distance A2, right? And this is how it is rotating at an angle theta, right? So for this, we need to initially find out, in order to write down the Lagrangian Euler equation. What is the Lagrangian equation? Lagrangian equation is nothing but the kinetic energy minus the potential energy, right? Lagrangian equation formula equation is nothing but the kinetic energy. It's a difference between the kinetic energy and the potential energy. So the kinetic energy is nothing but the sum of the rotating links and the sliding links, right? Kinetic energy is equal to sum of the rotating links plus the sliding links. And the potential energy includes gravitational potential energy, right? And the potential energy will include gravitational potential energy. Now, as per we know that Lagrangian equation is nothing but the difference between the kinetic energy and the potential energy. So, the kinetic energy is being determined with the term T, and the potential energy is being determined with the term L. So, here we have written L is equal to T minus V, that is kinetic energy minus potential energy. So, as per the Lagrangian equation, what we are writing with respect to the QI derivation, d by dt into dou L by dou Q1 dot minus dl by dqi is equal to T. That is T, where T represents the generalized forces, that is torque, associated with Q1, that is with respect to the torque and the force, we are writing this particular equation. With respect to the torque and the force, we are writing this particular equation, that is d by dt of dou L by dou Qi dot minus dou L by dou Ti dou Qi is equal to Ti. Right? So, this is how we find out, we write the Lagrangian equation initially. Now, we need to compute the Lagrangian and derive the equation, that is with respect to the kinetic energy, potential energy, Lagrangian function and equation of motion. So, as we are considering the kinetic energy for the revolution joint, we need to consider the rotational kinetic energy. For revolutionary joint, we need to consider the rotational kinetic energy, and for prismatic joint, we need to consider the translation kinetic energy. Right? When depending upon the type of the joint, right? Depending upon the type of the joint, the kinetic energy will be changing. If it is a revolutionary joint, we will be having a rotational kinetic energy, and if it is a prismatic joint, we will be having a translation kinetic energy. And when we come across the potential energy, we need to determine the gravitational potential energy. Right? When we come across the potential energy, we have to find out the gravitational potential energy, and this we have already written the Lagrangian equation, that is difference between the kinetic energy and the potential energy. And coming to the equation of motion, using the Lagrangian equation, we need to derive the equation of motion. Right? With the help of the Lagrangian equation, we need to determine the equation of the motion. Moving on to the third problem. Derive the equation of motion for a single link manipulator given the mass and the length of the link. Right? When we are having the mass and length, that is when we consider the mass and the length, that is distance, we can take it as the length. Right? We need to find out the equation of motion. Right? We need to find out the equation of motion. So, how will we find out that? For a single link manipulator. So, for this, first we need to consider a two-dimensional plane. Right? For this, let us consider two-dimensional plane. After that, the link is rigid with uniform mass distribution. The manipulator is rotating in a two-dimensional plane. First, we need to assume. We need to make certain assumptions that the manipulator will be rotating at a two-dimensional plane, and the link is rigid with uniform mass distribution, and the link has a mass m and a length l. Right? It is having a mass m and it is considered at a length l. Right? Now, the rotation is about a fixed axis, that is a pivot at one end and of the link. Now, considering the kinematics of this particular equation with the length, we are writing x centimeter is equal to the length by 2 of cos theta with respect to x axis, and with respect to the y axis, it is L by 2 sin theta. Right? When we are considering the x axis and y axis, we will be writing with respect to x, it is at the center of mass. With respect to x, we are taking it as L by 2 cos theta, and with respect to y-axis we are considering it as L by 2 sin theta, where theta is the angle of the link with respect to the reference, right? Now we have to find out the position. We need to find out the position also. So the velocity at the center of the mass is being taken as x dot, right? The velocity of the center of the mass is being taken as x dot, where theta is the angle of link, and we are writing it as minus L by 2 sin theta into theta dot at x-axis, right? And at y-axis minus L by 2 cos theta into theta dot, where the y-axis is, with respect to y-axis with the center of mass, we are writing it as the equation square root of x square plus y square, which is equal to L by 2 into theta. Right, and the kinematic energy is being considered. The kinematic energy of the link is being considered as T is equal to 1 by 2 mv square plus 1 by 2 I theta square, where I is the moment of inertia of the link, where we are writing it as I is equal to 1 by 3 ml square, right? Where we are writing I is equal to 1 by 3 ml square. Now substituting this V and I into the kinetic energy expression, T is equal to 1 by 2 m, right? T is equal to 1 by 2 m into L by 2 theta whole square plus 1 by 2 into 1 by 3 ml into T square, which where overall we are getting it as T is equal to 1 by 8 ml square into theta dot square plus 1 by 6 ml square into theta dot square, right? For the potential energy, we are writing it as V is equal to mgh, right? For the potential energy, V is equal to mgh, where h is the height of center of the mass, right? And we write h as h is equal to L by 2 sin theta, and V is equal to, since mgh, it is mg into L by 2 sin theta. Whereas when we are considering the Lagrangian equation, L is equal to T minus V, and we already have the value of T kinetic energy, and we already have the potential energy, that we are substituting this particular equation, that is L is equal to T minus V, that where T is nothing but, this is T, 1 by 2 m into L square by 3 plus L square by 4 theta square minus mg L by 2 sin theta, right? And the overall equation of motion, we will be writing it as d by dt. This we already know, right? D by dt into dou L by dou theta dot minus dou L by dou theta is equal to 0. In this formulation, we need to write the equation of motion with respect to the Euler-Lagrangian equation, where dou L by dou theta is equal to m into L square by 3 plus L square by 4 into theta dot, and d by dt of dou L by dou t is equal to m into L square by 3 plus L square by 4. So overall what we are getting, dou L by dou theta is equal to minus mg L by 2 cos theta, right? What we are getting, dou L by dou theta is equal to minus mg L by 2 cos theta is the equation of motion with respect to the Euler-Lagrangian equation. And the final equation of motion will be m into L square by 3 plus L square by 4 into theta dot plus mg L by 2 cos theta, which is equal to 0. So here what we are doing, we are taking m common and we are cutting it in, where this is being left over. It is L square by 3 plus L square by 4 into theta plus gl by 2 into cos theta is equal to 0. Where when we are considering these particular two equations, what we are getting, 4 plus 3 by 12 into theta dot plus gl cos theta is equal to 0, where we are writing it as 7 by 12 theta dot dot plus g by l cos theta is equal to 0. That is, this is the equation which describes the angular acceleration. This is the angular acceleration for a single link manipulator under the influence of the gravity, right? Under the influence of the gravity, we are finding out the angular acceleration for a single link manipulator, right? These are differences. So in this problem, first we need to find out the kinetic energy, then we need to find out the potential energy, then we will be writing the equation of motion with respect to the Euler-Lagrange equation, that is kinetic energy minus potential energy, and finally we will be writing the equation of motion, where we will be determining the acceleration for a single link manipulator with respect to the gravity, and this is the final equation which we will be getting. Right. So in today's session, we have discussed about how to find out the angular acceleration for a equation of motion for a single link manipulator with respect to the mass and the length. Right. Hope you have understood these three examples. So in the next session, we will be discussing further more examples which will add more knowledge to your subject. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.